Yes?
So, like, metals aren't atomically ionic. Like,
Okay, metals have some behavior that's kind of like atomic and kind of like ionic. When we talk about the structural particle of a metal, we call those atoms. Because for every metal atom or atom center thing, all the electrons are there. Just the outermost electrons are held loosely. Okay? They're all there. If you move one of two or three of those electrons from the outermost level of one of those atoms, you can't. That's what it wants. It behaves like a metal. It flows through there. The electrons can flow through there. But when the electrons move through there, the new ones always fill in where the old ones were. That makes sense. So you always have the number of electrons every one of those atom things have, but it also has some ionic sort of behavior in that the metal is attracted to the electrons, but the electrons are also shared with another metal. It's almost like covalent in a sense, except that in covalent bonding, those electrons that are shared are trapped in a certain region we call a bond. With metals, they're loosely held. Okay? So it's somewhere between atoms and somewhere between ionic because it's opposite charges attracting like ionic. The metal center, if you think of the electrons that are loosely held as being not part of that, you have kind of like ions. Okay? So those ions are attracted to the electrons. The electrons become the negative ion in that sort of context. So it is an atom, but it has some sort of like ionic kind of behavior. It's ionic in the sense, has the ionic behavior, in the sense that it is a truly crystalline structure. We don't think about metals being crystalline because when we think about crystals, we think about those things breaking really easily. Okay, we break them, they're done. But metals can bend instead of break. But if you talk about how the atoms are arranged in a very rigid and repeatable structure, one where you can, if you know where these set of atoms are, you know exactly how these also are arranged in that metal. They have a crystalline structure. So there's a lot of similarities with both covalent network and ionic crystal in some senses. So it's a, when we say it's structural particle as an atom, you know, it's kind of somewhere else. You know, not quite that. We don't have anything else. That's the best thing to call it. All right? Does that help you?
Yeah.
All right. Hope that's not too confusing. A lot of it's confusing? Well, now's the time to ask me about it. I'm waiting.
Can you?
Yes.
Oh, you can go ahead. Can you explain the dipole thing?
A dipole just means the kind of attraction there is between polar molecules. So polar molecule is polar because it has poles. And you can't really have one pole without the other, although theoretically, string theory and all that kind of stuff, they're looking for whether or not you can have a single pole. It's kind of like, that blows our mind. But molecules always have two poles. You have a positive end and a negative end, right? Okay? So if you have two poles, then you have a dipole, two poles, attraction to another molecule that also has dipole, arrangement. It just refers to the structure. Okay, so the question is about the illustrations having to do with London dispersion forces and how that comes about. Okay. Oftentimes, and this is a really, really super simple illustration, and we're looking at neon atoms here. Neon atoms have 10 protons. That's why I have a 10 plus charge, 10 electrons in the electron cloud. So this is a distorted sort of view of a neon atom, okay? So we often think about those electrons as being evenly dispersed within an electron cloud, okay? What? 9? Well, okay, so I left out an electron. It's all right. We think about the electrons being evenly dispersed, okay? But what happens is those electrons are moving around really, really fast, and they're moving around randomly. Although there's some reasons why they kind of tend to stay in one area or another, they still move around, okay? So at any given instant in time, if we're playing musical chairs with electrons, and the music stops, and instead of having them sit down, we have them just stop, okay? They freeze. So some kind of musical freeze chairs or something, okay? Then what you get is, from time to time, you're going to get an uneven arrangement, a unbalanced arrangement of electrons. Now, I've kind of overstated this, because there's going to be some electrons over here, but most of them are over here, okay? That's our idea. They're going to be kind of lumpy. They're not going to be all, spread out evenly, all right? They're going to be kind of lumpy in terms of where they're located. It's like the universe is lumpy. You've got groups of stars in one place and almost empty spaces in another, okay? So this is the same kind of thing that's going on here. Well, that creates a temporary and somewhat weak type of polarity, And it's very, very brief because it only exists as long as that uneven arrangement of the electrons. It's called an uneven density of electrons. Okay? A shift in electron density. All right? So we got this uneven arrangement or density of electrons creating a more negative end on the left side in this illustration and a more positive end over here where there aren't many electrons or very few electrons because it kind of exposes the nucleus over here a bit where the protons are. Those are positive. And so you create a negative end on this side and a positive end on this side. And so you've got a positive and negative end that can be attracted together through electromagnetic force. But because it's not permanent, and it's very brief, and because you have this dispersion of electrons and not really a permanent shift, it's a weak attraction. Much weaker by comparison than a polar attraction. You with me? Does that help you?
Yeah.
Okay. And we just used dots yesterday, I think, in our illustration, right? And we'll be spending some more time on this idea in a more complex way in this class, okay? But this was the simple idea to lay it out for you right now. Okay. I got two hands up.
Well, this is not really
Okay.
but you said there was going to be some on the positive side.
Yeah, I've kind of overemphasized the shift in electrons because there's almost never no electrons on the right side, for example. Okay. Yeah, I just kind of made it simple to grasp the idea. Okay. All right. Yeah. Jack.
Does this just happen with, what does this happen with? Everything?
Non-polar molecules. Actually, it happens with everything,
Okay.
but it's only pronounced enough to make a difference with non-polar molecules. If you've got a polar molecule, the polar parts of the molecule kind of take over. All right, because it's there all the time, it's stronger, it's more important than the non-polar part. We'll talk about that, how that relationship works in a few minutes, okay?
So this has some non-polar, and that makes it halfway the polar, okay, because that's a positive and negative?
Yeah, it's a temporary polarity. It's exactly what it is. But it's so fleeting that you couldn't call it strong. It's like it's there for a minute and gone. It's there. It's not there very long, but it's continuing all the time. So, it's kind of like they're gone, they're gone, they're gone. So it's happening, but it's not consistent. That's one way to think about it anyway. Huh? What's the point of it happening?
Yeah.
It creates an attraction between these particles. Okay, all the go ahead.
That just makes it unstable molecule?
It's not unstable, it's just not as stable in terms of the electromagnetic force attracting them as a permanently polar arrangement or an ionic arrangement or a metallic arrangement or a covalent bond. Okay, because it's not consistent, constant, all the time, where these others are always there. Okay? All right? It's like you have some friends you can depend on all the time, and some friends you can depend on some of the time, and some friends, if you can call them that, you can't depend on at all. Right? Well, this is like the ones that you can sort of depend on some of the time. Got that? To use a kind of a strange analogy there. All right. What's the next question? Any others?
So the London dispersion happens with dipole bond or
No.
different bonds?
London dispersion refers to the kind of attractions that occur with this kind of arrangement or shifting of electrons. Okay, London dispersion forces are the result of the uneven dispersion of the electrons within the electron cloud. Okay?
So this happens all the time with non-polar.
Yes.
Or does it happen with polar?
It does happen with polar, but the thing about it happening in polar is the polar stuff is consistent and stronger, therefore, so it's way more important than the London dispersion stuff. So it's like you ignore London dispersion if you've got a polar molecule.
Is that so this is for non-polar is the London dispersion, but then you said someone else called it something different. Would that
Van der Waals?
Van der Waals.
Yeah, there are Van der Waals forces too, which is very, very similar but somewhat different. I prefer to use the term London dispersion for this. If you want to be really picky about it, it's London dispersion that refers to how the electrons move around. It's the forces of attraction the forces of attraction are called Van der Waals attractions. Don't worry about it. Just call it London dispersion forces, okay? Because you see it in the literature that way. Yep.
There's not a different name for the attraction between non-polar and the ones that are polar. There's not a different name for it. It's just one.
Yeah,
of
this
the-
is London dispersion forces, and polar attractions are dipole-dipole forces.
Okay.
Attractions between two polar molecules are called dipole-dipole forces. The attractions between nonpolar molecules would be called London dispersion forces.
Okay, that confused me because I thought it was like, I don't know.
Well, this is a temporary dipole-dipole force,
Yeah, that's.
but it's
what-
temporary. So because it's temporary, we call it London.
Yes.
Okay, got that?
And you said, what was the one you said before that?
Dipole-dipole? Well, a dipole-dipole usually refers to having permanently polar molecules with two poles, dipole, right? And so there creates a permanent attraction there. This is a temporary attraction, but it keeps happening over and over again, really, really fast. So while it's not happening consistently, it is reasonably consistent over time. Okay? Not to stretch the point too far, I hope. All right? Okay, now again, guys, this is all theory. All right? It's all modeling. Okay? There's no math here. So if you aren't toying with these ideas and allowing those ideas to bounce around in your head, you're creating images in your head, you're running the video in your own head with this stuff as we talk about it, you're going to fail the test. Okay? Well, if it sounds easy, that's great. All right? Okay. If you're just sort of halfway paying attention and just writing down stuff when you have to, you're planning to fail. So just so you know. All right? Huh? Okay. Any other questions about the material in the packet? Yes.
So, when it says what kind of structures will undergo the kind of attractions London dispersion forces, would it be non-polar?
Yes.
Non-polar.
Yes. So London dispersion, nonpolar molecules. Okay. All right. Anything else? All right. So the question then is, what is this stuff in the very back here? All right. This stuff here.
I'm sorry.
Well, to understand this stuff, you got to go back a couple pages, starting right here. Okay? So, if we're looking here, if you look at the nonpolar covalent molecules and their melting points and boiling points, okay? Look at the range of melting points and boiling points. Well, let's just start with melting points because that's the first chart you were asking about over here. No. All right, here's nonpolar covalent. Well, that is right there the same temperature range as you find over here in the table. Okay, in table 1. This is the same temperature range here as you see right here. So it's comparing these temperature ranges. Okay, now here's the point with all that. If I just gave you this table and I ask you questions about, say something like this. Which one of these two substances is likely to have the highest boiling point? Calcium chloride or iron metal? Well, you don't have to memorize the boiling temperatures. Did I say melting or boiling? Doesn't matter. Let's say melting temperatures, okay? You don't have to memorize the melting temperatures of iron and calcium chloride to answer this question, because which one would you predict is actually referring to what's here. But you have to understand the ranges, okay? So overall, if we were going to take a bet, so think about playing blackjack at Atlantic City or in Las Vegas or something, okay? You're playing the stats, right? You're assuming if I've got this card and I've got this card, what are the chances I'm going to go over 21 if I call for another card, right? You're playing the stats. Well, that's what we're doing here. We're playing the stats. If it's a metal, overall, even though there's an awful lot of overlap, overall, metals tend to have a higher melting temperature than do ionic compounds, overall. So playing the stats, we'd say iron would have a higher melting temperature, right? That makes sense? That's all this is doing. All I'm doing is saying, okay, I'm making it easier for you. I'm not making you think quite so much by laying it out for you to show you how those temperatures are arranged. Okay? So overall, nonpolar covalent have the lowest boiling temperatures, or for that matter, the lowest melting temperatures. Okay? Because if you look, they're pretty similar, aren't they? The two charts. This is the boiling temperature stuff, and this is the melting temperature stuff. Now, there's a lot of overlap, but polar covalent molecular structural materials have a overall higher melting temperature. There's a lot of overlap, but there are higher overall. So if I'm playing the odds, I'd be betting on polar covalent substances or materials having a higher boiling temperature or melting temperature than nonpolar covalent. Yes? Okay. And if I were a betting man, I'm not, but if I were a betting man, I'd bet on ionic over polar covalent or nonpolar covalent, wouldn't I? Because it's way up here, and those are way down there, and so forth. Now, well, a while ago about the overlap, look at metals. Metals go from here to here. I mean, there's a huge range in melting temperature for metals. But if you were to average it all out, metals are just slightly more likely to have a higher boiling temperature than ionic. Okay? On the average. But not by much. You with me? And then you got covalent network. Those are like diamonds. That's a covalent network structure, where every carbon atom is covalently bonded to 4 other carbon atoms. Okay? So the structure of that carbon atom bonded to another carbon atom, where each carbon center is attracted to the pair of electrons it is sharing with the other carbon atom. So in between 2 carbon atoms here, we've got a pair of electrons in between, and those pair of electrons are trapped in a bond. Okay? They can't move around, or they can't move out of that region, basically. Okay? So they're attracted to those 2 electrons. Both carbon atoms are. But it's not just one of those. Every carbon atom has 4 of those. Well, that's a really strong structure. Okay? We had a day when we went over to Sea Wing and built some, what was it, marshmallows and spaghetti and tried to hold up some books, right? And what kind of structures won? What were the differences between those structures that won and the structures that didn't win?
We won, by the way. Ours was better.
How so?
We had like a foundation.
Okay, explain the foundation. How is your foundation different from other foundations?
It was a little stronger, I guess.
Why was it stronger?
Because we put 2 on it.
Okay, so you had more spaghetti noodles holding up those marshmallows to hold up the books, right? Okay, you had an interlocking structure, more of it going on. Well, that's like those covalent network structures. That every carbon bonded to 4 others in a 3-dimensional arrangement like that, that's very strong. So diamonds, you just about can't melt diamonds. Okay?
Can you then?
Well, theoretically, sure.
What do you mean here?
I'll throw it in the sun, it'll melt. Okay? Okay? All right. So, but turning it into a gas, yeah, you could do that too. But, you know, it's kind of hard to do, right? All right. Well, you boil it to get it to be a gas. Okay? Actually, after you turn it into a liquid, it's not really a diamond anymore anyway, because it has to have that tetrahedral structure to be a diamond.
What would it be?
Diamond juice.
I don't know. diamond juice. Carbon soup. I don't know. All right. All right. So anyway, all this does is sort of summarize some of the information, some of the pertinent information from that first table in this handout. Okay? That table right there. All right? Got it? So you need to be familiar with both the table and the 2 charts and understand how the concepts are related. Any questions? But while we're here, notice this has a figure label. So illustrations have figure labels. Graphs have figure labels. Review Unit 1. Figure labels for illustrations and graphs and pictures, okay? And tables have table labels. And table labels always go at the top. Figure labels go at the bottom. Okay, good. All right, now, that's enough about that. I've answered your question. Any more questions about the handout before I move on to my next subject I want to cover today?
What about the other 2 charts behind that?
Well, we're going to actually cover that today, actually, so that'll be good. He's asking about the other 2 tables. They're not charts. They are tables because they're formal tables. They meet all the requirements be a formal table. Okay, we'll get to that. Okay? All right. Everybody good? All right then. I want to talk a little about now, yesterday we talked about and pretty much centered our discussion on the strength of attraction between different types of these structural particles. There are 3 kinds of structural particles: atoms, ions, molecules, right? But there are 5 kinds of structural materials. So those 3 kinds of structures make 5 kinds of structural arrangements. Polar molecules and nonpolar molecules. So those are 2 molecules. You got ionic.
Atoms.
Well,
Is it metal? It's
atoms actually.
Atoms and then metal atoms.
Okay, ionic. Well, but in ionic compounds, you don't truly have atoms anymore because they're charged.
Yeah.
Okay, but metals, okay, I see what you're saying. With metals, you call them atoms, but they're really somewhere between the behavior of an atom and the behavior of an ion. Okay, and then you get those covalent network structures we talked about, like diamonds and glass. And remember, I said glass. We think about glass like the glass in a window, or the glass in the kind of glass you drink out of. Okay. But the only truly crystalline glass is that which cools really, really slowly. And that only happens in like volcanoes. Okay? So that stuff has a really high melting temperature and a really high boiling temperature. But the kind of glass in your windows, that has a much lower boiling temperature because it's not orderly and structured the way that crystal glass is structured. And when you go to the nice department stores and buy what they call crystal glass, quote unquote, it's not truly crystal in a chemical sense. All right? They just call it that. I mean, there's better glass and more crystalline, but not truly crystalline as what a chemist would call crystalline. All right? Everybody good? All right, then. Let's talk about the things that affect, then, whether something's going to be a solid, liquid, or gas. All right? Talk about things that affect whether something's going to be a solid or a liquid or a gas. So far we've been talking about the strength of attraction. Well, that affects whether something's going to be a solid, liquid, or gas. Because things with a stronger attraction together, they tend to stick together better. They make better solids, right? So covalent network structures are going to be solids because they really stick strongly together, and it's really hard to make them start moving around each other. Okay? Remember I did this little thing yesterday? You did this thing yesterday? We talked about these are solid particles, and they can twist and turn and wiggle and stuff, but they stay locked together in place. But then if you get them twisting and turning more and more, they start to move around each other, right? And then eventually, after moving around each other, they keep adding more heat to them. They move faster and faster and faster, and eventually they go flying away, and they become gases, all right? That was our fist bump examples of solids, liquids, and gas structures. All right. So what we want to do is look more in depth at the things that make things become solid, liquid, or gas. Okay, so these are factors that affect the physical state of a substance. Factors that affect the physical state of a substance. All right. So yesterday we spent almost the whole day talking about that strength of attraction and what structurally within those particles and having to do with those particles led to those stronger or weaker attractions between particles. So strength of attraction between particles affects whether something's going to be a solid, liquid, or gas. Strength of attraction between particles affects whether something's going to be a solid, liquid, or gas. Okay? That was kind of new yesterday, but it's not new today. So if you've got something that's a solid, how do you get it to be a liquid? You melt it. Well, what are you doing to melt it? Adding heat. Okay, we're putting heat into it. Okay? Now what does that adding heat do to those structural particles? Well, it doesn't it doesn't really weaken their attraction at all. But they're moving faster, and the momentum of their movement rips them apart. Yeah. Is that what you were saying?
ripping the bond in a way.
Okay, yeah. So if I'm moving them faster and faster and faster, you would think, well, eventually they'll move apart, right? That's what's happening. The faster I move them, the more likely they are to then turn into liquid, and then eventually turn into a gas. So factors that affect the physical state of a substance, and this is a review. This is not new to either this unit or this class. We've talked about these before. You've done this. You should have talked about this stuff in 9th grade, and a little bit less in a slightly more elemental way in 5th grade. Okay, so it has to do with how fast structural particles are moving. So how fast structural particles are moving will also affect, they're also a factor that affects the physical state of a substance. Does that make sense? Now we're going to get to a category we've not talked about in here before. And I hope it's not going to be too foreign an idea because we kind of touched on it a little bit yesterday and talked about London dispersion forces. Okay? Y'all got that written down? Can I go on? All right. So let's talk about molecules. Now, we're going to use nonpolar molecules to help illustrate this idea. Okay? We'll move into polar molecules in a minute. But there are very few spherical molecules. Okay? Very few spherical molecules. They almost don't exist. They're so rare. In fact, it depends on what you call spherical, I suppose, but they really are they're more lumpy. They have other shapes and things like that, but you almost can't have a spherical molecule. But for the sake of our discussion, I'd like to use a theoretical molecule that's spherical. Okay? You with me? So let's say I have two spherical molecules, and they're nonpolar molecules. And inside this spherical molecule, what's happening to the electrons? They're moving. And they're moving really, really fast, and they're moving randomly. So if the music turns off and they just suddenly freeze in place, where are you going to find them? Anywhere, randomly. And statistically, it's more likely they're going to be unevenly arranged than evenly spread out everywhere, right? Okay? So more often than not, you're going to have more electrons grouped up on one side as opposed to the other. Does that make sense? And so that creates a partially negative end on this side because electrons are negative. Temporary, but it's a temporary dipole. And this end to be partially positive. Well, if this molecule also has a similar arrangement of electrons, where most of them are grouped up on one side, this is going to be partially positive and partially negative here as well. And so we have everything we need for this molecule to be attracted to this molecule because of the opposite charges, and it's an EMF force, an electromagnetic force that's pulling them together. Okay, so these are nonpolar molecules we're talking about here. Okay. Now, let's imagine let's imagine we got molecules that are like Play-Doh. Okay? So we're not going to change the size, not going to change the mass. We're going to keep the surface area of the molecule about the same, but we're going to elongate it. We're going to go from having a surface area that's spherical to a surface that is more stretched out into more of a worm shape. Okay? So we get something like this. Now, without going too much into the detail of the way that force works, this electromagnetic attraction, electromagnetic force works, I want you to just think for a minute. If you throw a rock into a pond, what happens to the ripples? They spread out in a circular fashion, and as they go out, they get smaller and smaller and smaller, right? Force is a lot like that. The further away you get from the source of the force, the smaller and smaller the force is. And it drops not in a subtraction sort of fashion, but in a let's see, what am I thinking of? Exponential form. Okay, it drops exponentially as you go further out. So the amount of force as you get further and further away is way, way less every time, every little bit you move out from that object, okay? So if the surface area here of the attractive force is right here, the strongest force is going to take place right in here. The strongest attraction is just this tiny little bit right in the middle, right? And if you get more out here on the edges, there's way less force as you go along, right? So you can think of the strength of attraction as having to do with how much surface area can come in contact between these two particles. Are you with me on that? Okay? So that's not a lot of surface area that can touch. How much surface area can touch there? If it's a perfect sphere, 1 point, right? But how much surface area can touch here? A lot more by comparison. And so since the electrons in the same way are moving around randomly and chaotically and nearly very, very, very fast, then you're going to get electrons from time to time grouped up on one side and not grouped up so much on the other. And so overall, you're going to have a overall partially negative charge on this side. Whoop, I mixed that up. I should have had more molecules over here to make it do the right thing here, because I want positive and negative to each other. Okay? So let's take out some of the electrons. That's moved them out. Okay? Everybody good with that? All right, so now our negative side is going to be the right side, because the electrons are negative and I've grouped them up on the right side, which means that this side of this molecule is partially positive and this side of this molecule is partially positive. You with me? Okay? And so I've got more surface area. Those lines of force are stronger in between, more strength of attraction between those particles. Does that make sense? Overall, by looking at that surface area. Are you with me here?
So you said like attraction, it depends on the surface area.
It depends on the surface area. Okay? So the EMF force between these two particles, even though they're roughly the same size, same mass, same surface area, there's a greater force of attraction between these two kinds of particles. They're both nonpolar, but there's more surface area, more potential to have that change in density of electrons in that electron field. Okay, so you can have more chance for it to be pulled together by those London forces. Does that make sense? Okay. So what kind of molecules would have a shape like this, a worm shape like this?
Metal molecules.
Well, metals don't make molecules. Sigma bonds only refer to the bonds between atoms, not to the whole molecule. What shape of molecule, what kind of molecule do you know about that might have a worm sort of shape?
Potassium.
Think Unit 4. Think organic. Potassium is not a molecule.
Hydrocarbon.
What kind of hydrocarbon?
methane.
Methane is more spherical than it is elongated like that. Methane is kind of lumpy but almost spherical.
So it'd be like
Will be like long chains.
Yeah. Sure. Ethane would be really short. It would be more elongated than methane would. Well, decane's really long, isn't it? Pentane, hexane, heptane, and so forth. Does that make sense? All those could be these elongated sort of molecules. All right? So the longer the molecule, the more attractive force there is pulling them together. Okay? You with me? All right. I'm going to come back to this idea in a minute, but first let's go to something slightly different. Now, I've been using dots to show where electrons are kind of grouped up. For this next shape, I can't really do that. Yes?
Can you put like the first page you had up there, like 36?
Okay. So I can't show you the dots. We'll have to just talk about what they do, because I think these illustrations are probably enough for you to get the idea that when electrons get grouped up, you create kind of a negative part. Okay? Let's see if I can, I don't know how to illustrate this in a way that makes a lot of sense, but let's see if you can make sense out of it when I draw it.
that like a cookie shape to you?
It looks like
Yeah.
Like a weird frisbee, he says. How about a pancake?
Yeah, they have
I'll see the butter.
quarter. Yeah.
Well, pancakes don't have to have butter to be a pancake. Come on.
Buttermilk
All right, so I got two molecules that are not, no longer are they spherical, no longer are they worm-shaped. They're kind of flattened now. So think about your Play-Doh. Okay, you take a ball of Play-Doh. Okay, not much surface area. Lengthen it out into that sort of worm shape, more surface area. What about this? How does this compare by surface area? A lot more. Exponentially more surface area. Okay? So if the electrons moving around really rapidly, you got these places where they're grouped up more than other places, and if this side of this strange cookie-shaped or pancake-shaped molecule, this side is the more positive end, and the more negative end is kind of on the back side over here that we can't see. That's why I can't put the dots in there. It's kind of hard to tell what's going on. If you do that, you have way more surface area. Okay? So compared to these molecules, okay, how much more attraction, even though they may have the same surface area, the same size, same surface area, how would the attraction between these molecules compare to these?
it'll be greater than those.
Why? Why greater?
Because it has like the whole flat side.
A whole bunch more surface area. You know, like your hands, a whole bunch more surface area. Okay? That's what's going on there. All right, so this has even greater electromagnetic force pulling them together. These are still nonpolar molecules. So it's London forces, a shift in electron density, an uneven arrangement of electron density that's pulling it together. Okay? All right, let's see. We said that those long molecules could be any straight chain hydrocarbon like pentane, hexane, heptane, octane, nonane, decane, and so forth. Can you think of any molecule that will be more pancake shaped?
Graphite.
Okay, graphite or graphene. Okay, that'd be good. Anything else?
No.
How about comparing, which one of those two is the pancake shaped one?
The bottom one, the phenol.
The bottom one, the phenyl group, which is really a benzene. Okay, it's benzene.
But it's also
If it was a side chain on a long carbon chain, we call it a phenyl group. True. Okay. They have the same number of carbons. The benzene ring at the bottom there only has 2 less hydrogens. The hydrogens are really small, only 1 atomic mass unit. Okay. So not much difference in their mass, not much difference in their size, because this is, well, it's really more donut shaped, because the donut shape ensures even more surface area can touch than this could. This is more of that elongated sort of worm shape. Okay? That makes sense? And what is this called right here? What's the name of this thing? Hexane. What's this one called? Yeah, but that's not a benzene ring, because a benzene ring has double bonds all the way around. This is actually what else? Cyclohexane. So this is hexane, and this is cyclohexane. Okay? So this one has more electromagnetic force attracting it to another molecule of its kind than this one does. Okay? More electromagnetic force attracting this molecule to other molecules of its kind than this molecule would, even though they're about the same size, same mass, close to the same mass anyway. Okay, you with me so far? All right then. Now, before we leave off of this size stuff, because so far we've been talking about molecules that have the same size, we just change their surface area. Let's talk about size for a minute, okay? Which is easier, well, let's back it up and say it this way, which is harder to move? A Volkswagen or a freight train? Freight train. Why? It's heavier. Actually, it's more massive. Weight or heavy actually is a relative term depending on which planet you're on. Okay? Or whether you're in space or not. Because a freight train weighs the same as a Volkswagen in deep space. Nothing. Okay? Yeah, nothing. They don't weigh anything in deep space because there's nothing, no gravity. Okay? That's another point for another day. Take physics. All right. So, but the point is, it is harder, whether or not you're in deep space or not, it's still harder to move the freight train. Okay? So if I have a solid with molecules the mass of a freight train, would it be harder to break it up into a liquid than molecules that are the mass of a Volkswagen?
Yes.
Sure, because of their size. So size does play a part in getting molecules to move faster so that you turn them from being solid to liquid to gas, or slow them down enough, because their momentum is high whether they're moving already or sitting still. Okay, freight trains momentum's high. So momentum is how hard it is to get something to change its speed or direction. If it's sitting still, changing its speed or direction just gets it to move. Okay. If it's already moving in some direction, how hard is it to get it to change direction or to slow down? That's also has to do with its momentum. Okay? So momentum, which is really probably the best definition of what mass is anyway. If you take physics, they may define mass in terms of momentum. Okay? The greater the mass, the greater the momentum. Okay? All right. Huh? All right. So, let's go back to our Venn diagram then, and let's tie these two ideas we just talked about together. Size and shape also affects whether something's going to be solid, liquid, or gas. Does that make sense? Because that strength of attraction is what makes it or helps to make it a solid, linked together, wiggling, but not moving around each other, or move fast enough to become a liquid, or eventually fly apart and become a gas. Okay? So it's the size and shape of the structural particles that affects it as well. It affects whether you're going to have a solid, liquid, or gas, the physical state of a substance. All right? Y'all got all that? So, if you actually studied, as I asked you to, the handout, there it is. That's the discussion we just had. All right? So, this is explaining the stuff we just went through. Okay, we took more time to kind of make sure it hopefully congealed for you. All right? Helped you out? All right, so far, we've been talking about, up to this discussion here, we talked about what happens with the different shaped molecules. We're talking about the differences in attraction between types of particles, whether atoms are attracted in a certain way or molecules or polar or nonpolar molecules are attracted in a certain way. But within each of those 5 categories, especially between molecule categories, nonpolar and polar molecules, there's also a range of attractive forces. Okay? And it has also to do with the shape and the structure of the molecule. Okay? So let's see. Let's go back a little bit, maybe back to about Unit 3 and Unit 4, when we were starting to figure out the shape of molecules. Okay? And we figured out polarity of molecules. So you might need to go back and find your notes for Unit 4, okay, because you're going to need to know this stuff for the test. All right? All up here, it says. Okay, good. So let's see. I won't go through the way that you figure this out, but you should know how to figure this out, the shape of an ammonia molecule or any other of those simple molecules we did in Unit 4. NH3. And so if we have, they get arranged, when we arrange them properly and figure out how they should be arranged, we get this trigonal pyramidal shape. Okay? Question, is this a polar molecule?
Yeah.
How do you know?
Because
Uneven arrangement.
Okay, uneven arrangement is one of two conditions for our super simplified to the point of absurdity definition of how our determination of what polarity is, right?
And the difference between the electronegativity.
And the difference in electronegativity determining whether each bond is polar. So you have to have both, yes, right up here. Polar bonds, that's the two conditions. Polar bonds and an uneven arrangement of polarity. Not just uneven arrangement of bonds, but uneven arrangement of polarity. If you've only got one kind of bond, then the uneven arrangement of bonds would be uneven arrangement of polarity. But if you've got more than one kind of bond, then you've got to figure out the uneven arrangement of bonds. Got that? I mean, uneven arrangement of polarity. All right, now, so the question I have at this point then, we know this is a polar molecule because it meets both conditions. It's unevenly arranged, as all trigonal pyramidal shapes are, and it has polar bonds, and somebody mentioned the difference in electronegativity, and so a difference in electronegativity that is greater than 0.5 would give us a polar bond if it's a covalent bond. I'm looking for my references here. Now, in an honors class like this one, you don't get to use this reference, but this is where you can go back and review and figure it out as we go along. Nitrogen has about an electronegativity of about 3, and hydrogen has an electronegativity pretty close to 2, and so that's an electronegativity difference of about 1, right? And that's more than 0.5. So our bonds are polar, it's unevenly arranged, we've got a polar molecule. But I need to know which end is partially negative and which end is partially positive. How do I figure that out? The lone pair? The lone pair has an effect on it. We didn't use that in our discussions, okay? What was it we said helped us to figure out where the greatest electronegativity is? That's where the negative end is going to be located. Okay? Which one of these atoms has the greatest electronegativity? Nitrogen does. Okay? So what that means is, well, let's look at it this way. If atoms are houses and children are electrons, okay? And all the children that live in these hydrogen houses have nothing but board games, and their friend in the nitrogen house has an Xbox. Where are the kids going to spend most of their time? In the Xbox house, in the nitrogen, right? So the electrons, because kids are electrons, are going to spend more of their time up here. Electrons are negative. This is the more electronegative end, right? So this is partially negative up here. And grouped together, all these hydrogen houses down here make up the partially positive end of the molecule. And really, you can look at it in two ways. You can say the whole south end here is partially positive, or you can say each of the hydrogens is partially positive, and both would be correct, depending on context. Okay? All right. So if I have this nitrogen molecule, this ammonia molecule containing nitrogen, and I have another ammonia molecule nearby, and so I've got, this is a partially negative end, this is a partially positive end down here, okay? Then I've got an attraction between this molecule and this molecule, because that's a positive end, that's a negative end. So there's an electromagnetic force that draws these things together, okay?
Just like fit like on top of each other?
Well, as I've drawn them here, yes, fit on top of each other, yes. Okay? That makes sense? But this is partially positive and negative. It's called polar. It's a dipole-dipole force that's drawing them together. Okay? It's not a fully charged particle. It's a partially charged end on a particle. You with me? Okay. Let's compare that to, say, a substance that's built of these particles here. If we're looking at these particles here as having some attraction, and these particles here having some attraction, there's an electromagnetic force holding or pulling these together. Which one has the greater attraction between particles? This set or that set? That set. The one on the right. Okay? So the greater electromagnetic force of attraction is between these kinds of particles. All right?
Because they're not partially charged, they're charged.
Yes. All the way. Okay?
That's calcium and sulfate, right?
That's calcium and sulfur. Sulfur, right. Okay? How about we compare this set of particles and these two particles to this set of particles? Okay, there is an electromagnetic force attracting these two. Which one of these three has the greatest electromagnetic force of attraction?
Calcium sulfide.
Why? She's claiming these two have the greatest attraction. Why?
No, it doesn't.
I think it's
Sodium chloride?
Okay, sodium chloride. Why?
Because that's
It's what?
covalent bond.
No, this is both ionically bonded.
No, it's
This is simpler than you're making it, guys. Which one has the greatest electromagnetic force of attraction? So which one's greater? Greater electromagnetic force. Okay?
Alright.
All right. Now, let's add into this, say another molecule. Let's see here. How about we do?
So would that one be stronger than the dipole?
Well, I'm gonna let you answer that. Okay. So here's a couple of particles. All right. Let's look at the there is an electromagnetic force of attraction here. What kind of electromagnetic force of attraction is there between these two particles? So you're saying it's a nonpolar molecule, so it's a London force. Okay. Which is greater? Polar dipole forces or London forces?
Dipole.
Okay, so the greater electromagnetic force is here, and for that matter, it's also here and here, right? So this is the weakest of all attractions. That makes sense? These. The London forces. Okay, because it's a nonpolar attraction. It depends on that temporary shift in density of those electrons. Okay? And so there's even a greater electromagnetic force over here between these two ions too than these two polar molecules. Okay? All right, we making sense here out of this? Now, these are different categories. Although I pointed out there's a greater electromagnetic force between these are the same category. This is ionic. These two are ionic. Okay? So there's a greater electromagnetic force here because the ions have a greater charge. Okay, creating a larger force. Yes? Okay. But polar molecules also have differences in their attraction. Okay? Nonpolar molecules also have differences in their attraction. Right here? That's ionic. Okay, both of these on the end over here are ionic. This is polar covalent. This is just nonpolar covalent. Okay, this is the weakling of the bunch here. Just down at the bottom. That's the weakling of the bunch. Okay? And so, would you say, of these four, which one of these combinations will create a substance that has the highest melting temperature? Our melting temperature is getting to unlink from being stuck together to moving around each other. Huh?
Calcium sulfide.
Calcium sulfide. Okay? Which one would have the lowest melting temperature?
The hydrogen.
CH4. What's CH4 called? Unit 4. What's it called? No, propane. No. Propane has 3 carbons. Yes, methane. Yeah, methane. Meth, eth, propane, yes, and so forth. All right. Got to remember that stuff. All right. So there are differences. So while there's a range of attraction of force, creating higher and lower boiling temperatures, higher and lower condensation temperatures, higher and lower melting and freezing temperatures. Between ionic compounds, there are similar ranges for polar and nonpolar. Okay? We already know that, well, would this have a higher boiling temperature than this, or would this have a higher boiling temperature than this? Which one of these two right here has a higher boiling temperature? Ammoniums, or the ammonias over here. Okay? Ammonium has 4 hydrogens and a plus charge. It's a polyatomic ion. Ammonia has no charge overall, has 3 hydrogens. Yes. Yes. Okay. But let's look at some of these ranges, different ranges that occur within polar molecules for a minute. Actually, let's look at this. Here we go. Here are 2 molecules.
This is leaking.
As you look at these 2 molecules here, remember about the structures we talked about here, okay? And think to yourself and answer this question. Which one of these 2 molecules is likely to have the greatest attraction to other molecules of its kind? Okay. The consensus is that the bottom one has the greater attraction to other molecules of its kind. Okay? Why?
Because it has
The NH2 over here is a polar end. Okay? Now look. Let's look at the structures and how that compares to what we talked about earlier. Here's ammonia. And here's what's the name of this functional group? Unit 4? Functional group names? NH2, the most important functional group in our list, last one on the list, not amide, amine, okay? All right, so just think about it. If we took this chain right here, and we take that CH3 and pull it off of there, okay, and we take a hydrogen off of this ammonia and stick it on there, that's how we get this structure, right? All right? It doesn't change the fact that it's bent or it's trigonal pyramidal. Okay, all it does is put a carbon where the hydrogen is. Is it still a polar molecule, still a polar bond here?
Yes.
Okay, so the difference in electronegativity between nitrogen and carbon is in the polar range. So we still have a polar end over on this end of the molecule. You with me? So this is a polar end, and we got a nonpolar end over here as well. Okay? But because we have a polar end, that's a permanent difference in electronegativity and not a temporary shift in electron density, creating a temporary dipole. We have more attraction between this molecule and others of its kind than this one. Make sense? Everybody good with that? All right, let's add another one to the mix. Compare these 2 to the one I'm about to show you, or I'm in the process of showing you. Okay? Of these 3, which one is likely to have the greatest amount of electromagnetic force attraction between that particle and others of its kind? Huh? Think it's the middle one? You think it's the alcohol?
I think it's still the middle one because you said that's the strongest one just a second ago. But
No, what I was saying a while ago was that of these 2, this is stronger.
But you said the polar end, I guess.
I still think it's more.
You think the middle one's stronger? What?
You said it's like an amine group? Like,
That's an amine group. It's the most important of the naming, not the most important in terms of polarity, just of naming. On our list of functional groups, the amine group is more important than the alcohol group. Okay? But which one has the greatest attraction? Which one creates a molecule with the greatest attraction to others of its kind?
I'm still going to say.
All right, Timothy says alcohol. He's the odd man out right now. Everybody else I'm hearing saying the amine. But have y'all changed your mind, or are you still saying amine? Are you going to stand by your decision, or are you going to change it?
Stand by it.
She stands by it. He's saying alcohol now.
I'm going alcohol.
Okay, we got 3 people for alcohol.
What is alcohol?
Why? Yes. You go alcohol? You go amine? Alcohol? All right. Well, okay, don't quote the packet. Tell me why. Tell me why. Tell me why the alcohol would have more attraction. Tell me why the amine would have more attraction.
Because it's a negative charge connected to a positive charge.
They're both polar. This is polar and that's polar. Which one has the greatest electronegativity difference? Which one of the two has a functional group with the greatest electronegativity difference?
Alcohol. Oxygen is further from hydrogen.
Exactly. Oxygen is further than hydrogen on the periodic table. So looking at the periodic table of electronegativities, oxygen is further from hydrogen than nitrogen is, and the electronegativity is greater than nitrogen. So the difference between oxygen and hydrogen's electronegativity and that of nitrogen and hydrogen is greater. There's a greater polarity in the OH group. Okay? It's the last one that has the greatest attraction. All right, now, some people get confused by this. The nitrogen has 2 bonds to hydrogens. And they think, well, but if there's 2 bonds to hydrogens, wouldn't that overpower or take over and make it more powerful than one for oxygen? Well, we would have to talk about what's called vector addition. And when you add vectors, you don't add 2 and 2 and get 4. I'm sorry. All right, 2 and 2 never equals 4 in vector addition. So that's a little beyond the scope of the class. Okay, say what? What would it equal? It would depend on the angle of the vectors. Okay, so you can't think of it in quite the same way. All right. In this case, the electronegativity difference of the alcohol group, electronegativity difference in the alcohol group is so much more or so much greater than that in the amine group that this would be the more electronegative end, or not the more polar end. And so therefore there's more attraction between this molecule and other molecules of its kind than for either of the other two.
Well, these chains have always been added with hydrogen.
No.
I mean, added with
Okay, then it was chlorine and bromine. Okay, so anyway, let's look. How about this one? Let's compare these 3 to the next one here. All right, how do these compare? Right. The goal of science is to develop defendable arguments, meaning reasonable arguments that can be defended. Okay? And there's a defendable argument for both this molecule and this molecule having the greatest attraction between it and those molecules of its kind. Okay? If you argued for this one on a test, or you argued for this one on a test, and your reasoning was sound, I would accept either answer. Because right now, in high school chemistry, you don't have enough foundational information to be able to make an informed argument either way. I think you can make an reasonable argument either way. Okay? So your argument, sound argument. Okay? The one that nobody made for the alcohol in this class, that's a sound argument too, if they made it correctly. All right? You can argue either way. Okay? All right, now that's one more, and we'll move on to kind of a different category. Now we're going to have 5 different molecules here. All right, of these 5, which one is going to have the greatest strength of attraction between it and other molecules of its kind? Okay, we have an argument for the last one. Any other arguments?
so that has a does the
Well, but this is the kind of thing you got to go think through and figure it out. Okay, and the most reasonable argument, actually the only acceptable argument, is that the last one would have the greatest attraction, because it also has that most polar end, and you add to that an amine group with while it's also polar, so it's not quite as polar as that. So the combination of those two would make this last molecule, have the greatest attraction to other molecules of its kind. Okay? Now, having said all of that, which of these molecules will have the highest boiling temperature? So boiling temperature means we started out as a liquid, the molecules moving around each other. We're finally going to get them moving fast enough they completely separate. So which one's the hardest to separate? The bottom one. It's going to have the highest boiling temperature. Which one's going to have the highest melting temperature?
The bottom one.
The bottom one. Linking together, wiggling around like this in solids to moving around each other after they move faster and faster. That's going from solid to liquid. If it has the strongest attraction, it's going to have the lowest melting temperature, and therefore the other one's going to have the highest melting temperature. Does that make sense? Yeah.
Seems like the bonds are different. Like you tried to like melt it, would it melt at one time? Or
Well, this would probably all melt at one time. Okay, I know what you're asking. But what you're talking about, what I think you're talking about, we talked about yesterday, which is amorphous solids, where the bonds are all the same type of bonds, they're not the same length or arrangement, so that you have a different strength of attraction in those bonds. Okay, that's a whole different sort of category. We're assuming all the bonds are reasonably consistent. Okay, all right. So let's do another grouping here. How about if we compare these molecules? Of these four molecules, which will have the lowest boiling temperature?
The first one.
The first one. Why? It's not a matter of less bonds. They're not. It's not a bond. They're all sort of elongated in a kind of a worm shape. WORM, worm shape. Okay, the mass would have an effect because the more massive, the harder it is to get it to move around, right? But it's also the size because the longer the molecule, if it's a worm shape, the more surface area you got, right? So this would have the smallest size, the shortest of the worm lengths, the smallest surface area of all of them. It'll have the lowest melting temperature, boiling temperature, condensation temperature, and freezing temperature. Just a reminder. Boiling temperature is the same temperature as condensation temperature. Freezing temperature is the same temperature as melting temperature. Okay? Water freezes at 0 degrees C. At what temperature does water melt?
100 degrees C.
0 degrees C.
No, I'm thinking boiling. Sorry.
Water boils at 100 degrees C.
I told you.
At what temperature does water condense?
100 degrees.
100 degrees C. It's a matter of putting in energy or taking out energy, which is part of a unit that's about 3 more units away. Okay.